start? Do you want it to be do it yourself or talk to your friends? All in favor of do it yourself? All in favor of talk to friends? Okay. Talk to friends. Here's this thing is rolling without slip on the ground, and there's a point P on the object, and there's a point P on the ground, a point P prime on the object, and they're touching each other at this instant. Later on, when this rolls over to here, point P prime is going to be up here, and point P is still going to be back here. Or maybe back, who knows which way it's rolling. And it's rolling without, it's actually moving, it's not still. It's rolling without slip, and the question is what's the relationship between the motion of these 2 points, the 2 points which are at this point, at this instant touching in time? Are the velocities equal? Are the accelerations equal? Neither, both, all different combinations, or you can't tell. That's your vote. 1 minute to think about it. You can't vote yet. I'll work on that. Okay, 10 seconds left. 1, 2, 3, 4, 5, 6. 3 seconds left. 3, 2, 1, 0. And then we hit this button that says stop, and we see how the vote looks. How does the vote look? It looks like that. I think the right answer is B. So almost all of you got this right, so I'm not going to spend a lot of time on it now, but let me just say very quickly what the subtlety is in the issue. I found out in offers hours yesterday this is very hard to explain. So if you don't get what I'm saying, I don't think we have time here to just go over it and over it until it gets into your head. But let me just try it out. And you can just listen to the words and ponder them. This point can't have velocity up or down, or else it would be penetrating or separating. It can't have a velocity sideways, or else it would be sliding. On the other hand, if you calculate its acceleration, as it's rolling along, its acceleration is the same as the acceleration of g plus the acceleration of this point relative to g. And if this is, say, rolling at constant speed, it's accelerating. It has a centripetal acceleration towards the center of the circle. So even if this is rolling at constant speed, point P prime has a vertical velocity. So you cannot say that these accelerations match. On the other hand, if you say that the velocities match, that gives you a relationship between angular velocity and forward velocity. And that expression you can differentiate. And that gives you a relationship between angular acceleration and forward motion. Differentiating the expression you get by setting the velocities being equal to each other is not the same as calculating the accelerations. The difference between them is when we calculated the velocities, we were picking these 2 points here. When you think about acceleration, you're thinking about velocity at one time, velocity at another time, take the difference between the two, divide by delta t. For acceleration, if we took at this point, if we look at a later time, this point is moved, say just a slightly later time, this point is moved up to here as this is rolled forward. So this could have a vertical motion. It's not a vertical first order motion, it's a second order motion. That's why it's acceleration. But the velocity is changing of this material point. Whereas when we calculated this velocity formula, it was for the relationship between the velocity of this point and this point. When we differentiate that formula, we're calculating what happens about the relationship between this point, and we're not using the same material point in that difference. So the derivative of the formula we get by matching velocities here is not the acceleration formula. Now it happens that the tangential component of the acceleration matches, but that's a discovery we make by that differentiation. That's not a fundamental result. Okay, So I'm going to leave that at the way it is. Next, I wanted to give a sort of brief review. Since we have a prelim tonight, I think it's an appropriate time to sort of stop and think about the logic of the course, what's happening here. This will be very much the same thing I did in the very first lecture. I'm going to try and do it a little quicker than I did it in the first lecture, but you can go back and look at the video of the first lecture or the notes of the first lecture, and it should be about the same idea, but now you should appreciate it more. So one thing is that we have skills that are going all the way through the course, like MATLAB, ODEs, vectors, and we use those all the way through the class, but they're useful outside of the class. You learn them before the class. You're going to use them in later classes also, even if you're not going on with classes that are technically dynamics. Then we have the basics, which apply throughout the course, and one of them is this thing which I call the 3 pillars. And I think it's time for you to go back and look at those 3 pillars and see that they actually... Oh, you guys didn't see how you did on the quiz. This is why I didn't go on. You mostly got it. So those of you down here who didn't understand what I said, ask your friends, go to office hours this afternoon, read the book, look at the lectures. Okay, we have the 3 pillars, which I suggest you stop and look at, because the claim is that all mechanics problems, dynamics problems, and statics problems have these 3 aspects to them, which are material properties, and that's the most intuitive. That's chewing gum versus springs versus dash pots versus air friction, coefficient of restitution, coefficient of friction, and so on. There's geometry, and you've been working with the geometry aspects of mechanics since you started learning geometry, probably in 3rd grade. And then there's the laws of mechanics. And any problem you do has these 3 pillars in them, and you have to stop and look at them, and you should be aware when you're using one or the other. And the geometry comes in especially in this later part of the course, as you should start to see. So then we have the organization of the course. And the way we organize the course is first we looked at particles, and we looked at free particles, what I call free particles. And what do I mean by free? Free means that force is equal to some function of position and velocity. But if you know the state of the system, and in dynamics the state is the positions and the velocities, if you know the state of the system, you can calculate directly the forces using these material properties. And then we did these free particles in 1D, in 2D. 3D is just as easy. You shouldn't think of 3D as being a harder case in the case of particle mechanics. Then we started a new section of the course, which is dealing with constraints, and that's the whole rest of the course. And the whole rest of the course is dealing with constraints. So what's the issue with constraints? In case you hadn't noticed, it goes like this. These are problems where you have to go to some trouble to find or finesse constraint forces. So these are problems where you cannot just use F equals ma on a particle and then all of a sudden you have differential equations to solve once you put in the material properties. These are problems where there are forces involved which depend on accelerations. But accelerations are what you're trying to find, so the constraint forces and the dynamics are all tangled together. And these problems started out with pulleys. And this is just the simplest example that I could think of, and that's why we put it first, of constrained motion in one dimension. So you just get the idea that you have to put geometry somehow explicitly into the problem, separate from the laws of mechanics. Now the next big constraint is a rigid object, and that's lots of constraints. It's all the different interactions inside the object to keep the distances between the points equal to each other. Now in the case of pulleys, we set this all up so you could find the constraint forces or not. Those are all part of the same equations. You can do some pulley problems where you never have to find the tensions, but you can. In the case of the rigid object, all we did was finesse the internal forces. And this led to concepts like angular velocity and moment of inertia. These are ways of dealing with the overall motion without getting into the details of the motion on the inside and without dealing with the constraint forces on the inside. So for rigid object mechanics, we finesse finding the constraint forces, the forces that make the object rigid. Now within this rigid objects, we did just a sequence of harder and harder problems, which were straight lines, circles, and then general motion, or general motion in 2D. 3D we're not doing in this class. Once you've got this idea, then you're in a way back in this situation where we were over here. That is, there is this rigid object constraint which we have to finesse and understand, and we do that by summarizing all the motion with angular velocity and summarizing the mechanics with this moment of inertia. But once we have that, we have some simple equations for a rigid object, and then we can just put any forces on it, and then we can do arbitrarily difficult problems with the rigid object, like that problem I did in lecture with the spring and the thing dangling around, and you had one in homework like that too. Very difficult motions, but they are in a sense like free motions of a particle. We added constraints to get a rigid object. Now we understand rigid objects. Now we get free motions of a rigid object. Now what we want to do is have more general constrained motions of rigid objects. And that's where we got to things like rolling, or this new gun and things like that. And that's where we're going to go for the rest of the course, is just dealing with more complicated constrained problems of rigid objects. So these problems are to this general free motion of a rigid object, like, in a sense, pulleys were to the free motion of a particle. You understand F equals ma for a particle. You can do lots of particles. We understand F equals ma and m equals I alpha for a rigid object. We can do lots of them if they're connected by springs or friction and things like that. Then we want to constrain them in ways like rolling or double pendulum or parts moving relative to each other, and then it gets complicated. The geometry gets complicated. So the whole hard part of the class from here on in is dealing with the complicated geometry of constrained motion of rigid objects and particles. And this is an example of the subtlety and difficulty that we have coming in. Okay, any questions about the overall organizations of the class? Does that make kind of sense what I said there? I think there's some new things here. Like, in some sense, you know, if you got an A+, you got a super A+ in physics 112 or the equivalent, in some sense there's not much new in this class. But I think even if you did get an A+ and A super plus in physics 112 and could do most of the exam problems in this course, these sort of aspects of organizing the course by thinking about these three pillars and thinking about free motion and constrained motion, I think that just way of thinking should be new for you. Okay, because the lab guy brought this demo down today, I'm going to show you this demo today as a motivating example, but I'm not going to get into the details of this example. I just want to show it to you. You can remember it, and then we'll talk about it as something to calculate next class. So let me just present this as a motivating example for machines and so on. And the reason we want to study machines is because we're engineers, and the way we're going to study them at least one way we're going to study them is with this so-called slider crank mechanism. So this is one of the labs which you would have done if we had done lab this semester. It's been part of the labs in the course for 35 years or something like that. Okay, so let me show you conceptually what this mechanism is. It's called the slider crank. Conceptually, there's one part like this. There's a piece like this, which goes like this, and it goes in circles like this. And this piece is called the crank. And then there's a piece over here which slides back and forth. And this piece is called the slider. And this piece makes this piece move. And the way it makes it move is with this extra piece over here. And this piece is called the connecting rod. And this collection of hardware is inside every car, every boat, every machine. It's not every machine because there's turbines, but every machine with cylinders. So a simple example of that is a lawnmower engine. So inside here, when this lawnmower engine goes around, is the slider crank mechanism. So I have my volunteer. Let me show you how the mechanism works. Here's a mock-up of it. Let's see. You want to tip it up as far as you can go without having a fear of it falling, which I think is wait till the force starts to get small again. You happy there? Up here. Hold it up there. Okay. So here's a hinge here, and this piece here can go in circles, and this is the crank. Bicycles have cranks, car engines have cranks, boat engines have cranks. If you look on the web and look hard, there's a picture of me standing on the crank of a ship engine from a newspaper in Finland. And the crank is a gigantic piece. It's like way bigger than I am in a ship engine. Okay, so crank is, maybe I'll find it for you so you don't have to, I do the ego surfing and you don't have to be that interested in me. Okay, so the crank is this thing that goes around and around in circles. Here's the connecting rod, and here's the slider. In this case, it's drawn as a big long thing, but it's a way of representing this constraint. There's two ways that this thing can be used. One is the crank can turn the slider, or the way it's actually used in most engines is the slider pushes the crank. And because the slider is a piston in the engine, and it's exploding back and forth and pushing the crank around. And you'll see there's a problem. If you don't time it just right, it flips around and goes backwards. And that's why it's nice to have engines with 2 or 3 or 4 or 5 or 6 or 12 cylinders, so they have a bunch of cranks all with different phases, so that as they explode, the direction of the engine is not strange like this. But those of you who've dealt with model airplanes, who's played with model airplanes? You know, raise your hand if you have. Well, those are one-cylinder engines, which are like this one. And they're old boat engines, which are one-cylinder engines, and old plane engines, which are one-cylinder engines. And those engines, if you start them just wrong, they go backwards, because you can make this thing go forwards or backwards. And then you have to stop it by sticking a stick of rubber in there and start all over again. So once it's going, you can keep it going forwards if you time it right. But if you do something bad in the timing, it'll even pop around and go backwards. Okay, so either way, there's a relationship between this rotary motion and this linear motion. Okay, that backwards thing. Who raise your hand if you do model airplane engines? Those small group of people. Just a minute. I thought there was like 8 of you who said you did model airplane engines. It's dropped way down. Model airplane engines. It's down to 0 now. Raise your hand if you played with those engines. Okay, did you have that experience of it going backwards sometimes? Okay, yes. Just the population that agrees with me is faded, but they do agree. Okay. Here's a lawnmower engine. This is a real lawnmower engine, but it's been taken apart. You can tip it up, but it'll be less tiring if you tip it up more. And this lawnmower engine can go round and round. Inside here is a piston that's going up and down. On the bottom of that piston is a connecting rod connected to a crank here. And probably almost all of you have something like this in your turbines for 225. Is that correct? Just raise your hand if you've got something like this in there. You don't have something like this in there? You haven't got that far in the course yet? Okay, well anyway, you have something like this. So here's this piston. It's supposed to be, it goes bang, there's an explosion that pushes the piston down and turns this around, and you can't really see very much, but it goes round and round, makes noise. You can tell that something's happening inside because if I drop a penny in there and then make this go round and round, eventually the penny spits out. So you know something's happening in there. Okay, so what's the deal here is you would like to find out what is the motion of one part given the motion of another part. So for example, when this goes round and round at constant angular velocity, this thing is not moving in a sine wave. In fact, it gets quite far from a sine wave if I make the crank length and the connecting rod length close to each other. On the other hand, if the crank length is much less than the connecting rod length, it's close to a sine wave. So you'd like to be able to calculate what these motions are, and that's meant to be a motivating example for you to think about machines and the geometry of this motion. Now, what is that relationship between this motion and this? It's a geometrical thing. It's not a mechanics thing. But to do the mechanics of this, you have to put in the geometry. Whereas the material properties, the third pillar in here, is hidden because in a problem like this, the material properties are hidden in the assumption that we make that all the parts are rigid and frictionless. It's a limiting case of material properties. Okay, any questions about this example? Okay. In order to understand machines like this, one way to understand them is to think, well, this piece, this connecting rod, which has this very complicated motion that's connected to two different moving things, is to try to make our understanding of that connecting rod simple. So what we do, one way of doing things, is we get on board the crank, we turn our bodies with the crank, our brains with the crank, and we only look at the motion of the connecting rod relative to the crank. So relative to the crank, and I mean relative in a very deep way, that is that you're on the crank, you're turning with the crank, all you see is the connecting rod spinning in circles about that hinge point here. So one way of understanding motion of complicated machines is to get on board the different parts of the machine and look at the motion of the next part relative to the one part. And that's this concept of relative motion. Getting on board some little machine part is hard, so I'm going to motivate that by an artificial example, which is my truck. Now I'm going to start that example now. Okay. Any questions about this, or about where we're going, about the organization of the course? Just one question about anything, just to make everybody happy. You have to ask one question. Yes. If you ask the question, Professor, is this going to be on the exam? Then I kill you. Any other question? What? How am I doing today? I sort of woke up a little anxious this morning for no reason that I can figure out. I don't really know why. And yourself? Okay, I think we're done here. What? You're tired. Yeah, I'm not really tired. I've just sort of got some funny anxiety. Okay, so now we're going to start this concept of relative motion, and this is just going to be in the course. Doesn't mean we use it for every single problem, but it's going to give us a set of tools that we can use from here on in. And I have to warn you, this is by far the hardest thing that we will have done all semester. I am not going to start this by doing a lot of theory as in derivations. I'm going to try to get you familiar with the terms in the formulas and what the formula says. If after you're comfortable with the formula you want to understand how to derive it, you can come to office hours, look in the book, read about it on the web, or so on. But I think it's not that productive to do it in lecture. More important, at least to start with, before you get to the theory, is just understand the terms, understand what I'm talking about. Okay, so the idea is, given motion of a rigid object, And by that, I also mean a moving reference frame. And given the motion relative to that object, you want to answer this question: find things about motion in the fixed frame. And what do I mean by things? I mean position, velocity, acceleration, stuff like that. Okay. So my first car was a pickup truck, and I think it's easier for the brain to have the moving reference system be a kind of big thing rather than a little machine part, so you can sort of get on board in your mind and you can think about it that way. So my first pickup truck was a 1963 Ford F100. It cost $70, and I tipped it over when I did a mechanics experiment one time. Want to see a picture of that? I happen to have a picture of that. Actually, I'll find the picture while you're copying stuff on the board later on. Okay, so we have some fixed frame. And you want to draw this big, really draw this big. The rule, don't crowd your confusion into a small picture, really applies to problems like this. Okay, so I have this pickup truck. We're looking down on it because we're only going to do this in 2D. And the reason we're using the pickup truck is so we can imagine getting on board, sitting in the bed, the back of the pickup truck, and not seeing the outside world, so we can know what we mean by getting on board. So here's the pickup truck. And it's got this front part, and it's got wheels and stuff like that. Okay. So we're going to imagine that we can get on board this pickup truck, and we're going to be keeping track of some particle P, which is moving around in the pickup truck. Now that could be a piece of the engine moving around. It could be your pet dog running around in the truck. It could be an ant crawling on the bottom of the truck. Eventually we want to know about the mechanics of something or some collection of things, and one of them we're going to call P, and that's moving around in the truck. Now as this moves around in the truck, we can keep track of it in a coordinate system which is in the truck, which I'm going to call I prime and J prime. And what's different about this coordinate system than other coordinate systems we've been using for the most part, polar coordinates are an exception, is that this coordinate system is rotating with some angular velocity omega. Or we can call it omega, by which we mean, if we're going to use a fancy notation, the angular velocity of the truck relative to the fixed frame. So if I just write a single omega, it means angular velocity is something. If there's only one thing to keep track of, we don't have to put all the subscripts. If there's bunches of different parts, we have to say the angular velocity of what with respect to what. And here we're talking about the angular velocity of the truck with respect to the fixed frame, which is the rate of change of some angle here, say phi. So this would be equal to phi dot k. Now while we pay attention to this particle, we can keep track of its position, and here's this vector, which is the position of P with respect to O prime. Meanwhile, this point O prime, it has a position vector too, and that's the position of O prime with respect to O. And if we wanted, we could use polar coordinates even in this rotating reference frame, and we could keep track of this angle here, theta, and this thing r here. And then actually our overall object of interest is this arrow here, which is the position of P with respect to O. So now we can think about the motion of this particle lots of different ways. We can look at how its x and y coordinates change in time. We can look at how its x prime and y prime coordinates change in time. We can look at how its r, I should actually call this r prime and theta prime coordinates change in time, because meanwhile I've got some theta and I've got this radius r. I can look at how the theta and r change in time. I can pay attention to how this point changes in time, all different things, and we're trying to find the relationships between those things. Now, if I write every relationship between everything, it'll take forever. But there's some basic relationships that we can use and then plug in one or another coordinate system as we need to. The basic problem that we want to think of is we want to, generally, this is not always, but this is just generally the way we want to think about this, is we want to think as given our x prime, y prime, x prime dot, y prime dot, x prime double dot, y prime double dot, r prime dot, theta prime, I'll spell that right yet, theta prime dot. So we want to think of as given is the motion relative to the truck. That's all this stuff. And also given is x of O with respect to, of O prime with respect to O, y of O prime with respect to O, x dot of O prime with respect to O, y dot of O prime with respect to O, x double dot of O prime with respect to O, y double dot of O prime with respect to O, omega dot, omega double dot. And all this stuff is the motion of the truck. And we can think our main goal is to find the position of P with respect to O, the velocity of P in the fixed frame, and the acceleration of P in the fixed frame. Now, there are lots of ways to think about this. There are lots of correct ways to think about this. So if I show you one thing, it doesn't mean another thing isn't right. Yes? Over here. T for truck, F for fixed frame. Let's see if I can find, think about a question, copy it down, think about what's not clear up there, and I will find you a picture of my truck. Get down here, see. Maybe I won't find you a picture of my truck. Where's my truck? I've lost my truck. Sorry about this. This is the most fascinating lecture you ever saw, isn't it? Okay, finally. My truck. So I was on Bostwick Road over here. This is my neighbor who picked me up after I was hanging from my seatbelt there. And she drove me to class, taught at this class or some class like this. Now, this was an experiment a little different from what I'm talking about in class today, but in the reach of what we could do in class in a few weeks. Anyway, I was doing a little mechanics experiment, and I drove off the road and tipped over my truck, and it cost more to fix than it cost to buy. Any questions about my truck? Yes? The experiment, I could give a whole lecture on this if we have time sometime. The experiment, actually, this is a whole lecture on it. I just showed you a piece of it. The experiment is what about the stability, the directional stability of the truck if you lock the front brakes versus locking the rear brakes. I didn't really think it through very well, is the problem. I hadn't done the calculation. I wasn't actually that interested in dynamics at that point. I was doing earthquake mechanics. I just thought, usually I step on the pedal and skid, and that's kind of fun. What happens if I pull the emergency brake instead and skid? And it was kind of fun, but it was different. Who knows that thing? Yes? Oh, strange. Yes?
What's to make a double valve?
It's a little mistake in the brain. Okay, next. Okay. So one way of dealing with these things is to write the position of P with respect to O is equal to xi plus x, this is O with respect to O prime with respect to O, and I'm just going to leave off the O part, and this is j hat plus x prime I prime plus y prime j prime. Then if we want to find the velocity of P with respect to O, we take d by dt of this whole expression. And then if we want to find the acceleration of P with respect to O, we take d by dt of the velocity of P with respect to O. And this is fine. This is not wrong, and some people like to do problems like this, and this is perfectly correct. When you go to do this, though, the calculation is not as straightforward as it looks, because you have to take into account that I prime is equal to I prime as a function of t, and that j prime is equal to j prime as a function of t. So when you do that differentiation, you have to differentiate those time-varying unit vectors, which we are going to do in this other approach also, but we're going to do it a little bit more indirectly. So now here's what we're going to do. We're going to say the position of P with respect to O is equal to the position of P with respect to O prime plus the position of P prime with respect to O. Now this one, if anybody asks us, is x prime I prime plus y prime j prime. Now what we're going to say is the velocity of P with respect to O is equal to the velocity of P with respect to O prime plus the velocity of O prime with respect to O, and this is wrong also, that's O prime with respect to O, plus the velocity of P with respect to O prime. Now, this thing has two different lives. it's also x of p with respect to O prime I plus y of p with respect to O prime j. So this one position vector, the position of p with respect to O prime, we can write in the fixed coordinates or the rotating coordinates. So this velocity, if we want to know the velocity, we get this by differentiating the second of those expressions, and that's the velocity of p with respect to O prime is equal to x dot of p with respect to O prime plus y dot of p with respect to O prime, I and j. Now after a while, we're not going to be allowed to keep writing things every different way because it just gets more and more complicated. So now we get to the first interesting formula, which goes like this. It says the velocity of p with respect to O is the velocity of O prime with respect to O plus, and now we're going to invent a thing that we're going to call v relative. And this is going to be the velocity of p relative to this truck frame. So t means the truck frame. So the velocity is going to be the sum of two velocities, but this thing has this funny definition. The velocity of the particle in the truck frame is going to be defined as the rate of change of x prime times I prime plus the rate of change of y prime with respect to j prime. So this is the key important concept, which is the velocity relative to a frame. Now this formula is actually not correct yet, so let me just leave it with a plus here so that you don't think we're done. Okay, so the key concept we're going to use is this concept of relative velocity. And relative velocity now is not going to mean subtract. Until this point in the course, whenever you heard the word relative, it meant subtract. Now, relative is not going to mean subtract. It means a more subtle thing. It means the velocity that you would see if you were, I'll get to you yet. I'll remember even, so you can put your arm down. The velocity you would see if you were on the truck and you didn't know you were on a truck. You're just looking around on the truck. So we're going to get back on this truck. We're going to imagine there's high walls on this truck. That's why I like to use a truck instead of machine part. You're sitting here. You don't feel the truck moving around. You just measure distances in the truck. You keep track of where this particle is. And if you see the particle moving in the truck, that means like crawling around or moving relative to the parts, then you say it is a velocity relative to the truck. And that velocity you can think of as having an x prime component and a y prime component. That's the velocity you see in the truck. Now that's not the velocity you see out here because the truck is moving. And it's also not, you can't just add these two to get the velocity at this point. In fact, that velocity, that relative velocity, is not the velocity of this point relative to this point measured in this fixed frame. How do you know that? Well, if this point was a bolt on the truck and not moving at all, back here in our way of thinking from earlier in the semester, we have the velocity of this point relative to this point instead of going in circles around that point. So the relative velocity of this one relative to this in the fixed frame is what we get by thinking of this as going in circles if it's bolted to the truck, whereas the relative velocity in this new way of thinking relative to a moving frame is 0. So we don't actually get the right answer by adding this new relative velocity to this velocity. Why bother to bring in a more complicated concept in order to get a more complicated formula? It's because it will help us with some problems. So what's missing here is this correction, which is the angular velocity of the truck relative to the fixed frame crossed with the position of this particle relative to O prime. This is the correction. This is what we get for the velocity if there was no relative velocity. So what you can do to figure out these three terms is imagine three situations where each of the terms is needed, and it turns out, because God is good, that the math of this derivation gives you the sum of the three things you would get separately. Okay, now what's your question? I cannot hear you. Do I have a P prime on this board? That is correct. The prime was misplaced. Okay, so this is the first big formula. Then we'd like the equivalent formula for acceleration. And I think I'm going to skip that because we're basically out of time. So any questions about, just take 1 minute and stare at this formula and see if you understand the terms in this formula. Yes? Where? Which term? Just shh. Be quiet, quiet, quiet. What's the question, please? This is the velocity of P with respect to O without a prime, another typographical error, is the speed of the truck, the velocity of the truck, plus the velocity of the particle as seen in a rotating, moving frame in the truck, plus the velocity you get by realizing the point P is spinning in circles around O prime. So even if the back right corner of the truck is still, and you pounded a giant spike through the truck into the ground, the truck could still be spinning in circles about that point, and there's still that point P would still have a velocity even though it's a bolt on the truck. You take those three concepts, add them together, it gives you the velocity. You have a test tonight, go to either room. If one room fills up, we send you to the other room.